Today we're going to talk about the second approach in a project of assumption physics, physical mathematics, and just to rehab a sort of high-level pictures. Let's go through the first couple of slides again. The main goal of the project is to identify a handful of physical starting points from which the basic law can be rigorously derived. And the issue that is going to be the theme of today is that you can't really do that without really rebuilding all the mathematical structures, or even the most basic ones, because you can't expect your assumptions at a high level to be clear and fully define what you're doing if you're not doing the same thing for the low level. Like, you can't sprinkle meaning and correctness on top. You have to do it at the most fundamental layer, and then grow the things consistently. And just to remind ourselves, the goal of the standard view in the foundations of physics is really that physics has to find the true law of the universe, the one that tells you how the universe works, what are the building blocks of the universe, and how they're put together so that you can get the correct ontology of the universe. You can solve all the problems that we have currently in philosophy and so on. And then there is this sense that that's the real physics, and everything else is an approximation. And by working on this project, we have a different view because of the results that we've been getting. We are going to see today, for example, that assuming experimental verifiability, the requirement, the physical requirement, leads to the existence of topologies of single algebra. This to the requirement of topologies at sigma algebra at the mathematical level, that geometrical structure are equivalent to entropic structures, which are not typically seen as fundamental building blocks of the universe, that Hamiltonian evolution is equivalent to assuming a deterministic and reversible evolution or isolation, and independence of degrees of freedom. And isolation is always an assumption, is not something that you can do and take for granted that it's actually 100% true. And if you add this other assumption of kinematic equivalence, you recover massive partial and flotation forces. So the overall results that we are seeing is that the physical requirements and your assumptions that you put on the system that you're studying actually drive most of the theoretical apparatus. And so for us, it's a lot more productive to say that the goal of physics is to find models that can be tested experimentally, because then we start with models and an assumption of the model and derive a mathematical structure. While if we say that we are actually describing the true law of the universe, we wouldn't have a way to recover all the things that we need to recover, right? We would have to find a different way, and I have no idea even if you can do it. And this approach instead works, so let's continue with the approach that works. And so really what we want to set up, and we're going to see it a little bit more precisely in this series of lecture today, in talking about physical mathematics, that we basically want to develop a theory of physical models in the same way that the foundation of math essentially describes what it means to do math, what is a proof, what is a set of axioms, what can you prove in a set of axioms, or the foundation of computer science, defines what is a computational machine, what is the models of computation that you have, what can you prove, what you cannot prove, what you can transmit, what you cannot transmit. We basically want to have the same feel as a foundation of physics. We want to say, what are the requirements of a physical model? What is a physical theory? What can you do? What you cannot do? What is the space of the possible physical theories? And so we want to have first a set of general physical principles and requirements that all physical theories must satisfy, because they all need to be experimentally connected to experimental verification. We need to be able to define systems. We need to be able to define states. We need to be able to define processes. And therefore, there are some basic requirements to be able to say, okay, I have a system that it's sort of separated from the environment. I'm doing some things. So there are choices that you have to make, and we need to be able to understand what those choices are. And then basically for those general principle requirements, you get a general mathematical framework, a set of definitions that are always valid in any theory. Right now, the notion of states in classical mechanics, in quantum mechanics, in thermodynamics is completely different. There is no like a most basic structure, right? That would satisfy all of them. You do everything differently. Instead, what we'd like to have is a sort of, if you're a software person, we want to have a super class than everything else that inherits, right? It's a little bit, as I said yesterday, it's like having the set theory of physics, and then everything is a set and everything inherits those basic properties. And then once we have something that it's in principle always valid, we can generalize the theorems that as much as we can in this general mathematical framework. And then we can take specific assumptions and find classical mechanics, quantum mechanics, thermodynamics, field theory, and possibly new theories as a particular instantiation of the most basic structure plus additional requirement and plus additional features. So that's basically what we want to have at a high level. And as I said yesterday, there are two approaches that we have. The first is reverse physics, with the idea that we take the physical theories that we have that are described very mathematically, and we try to find a set of principles so that we can start thinking more about the physics than the math. And physical mathematics is exactly the opposite approach. We start from scratch. We start with the physical requirements and physical idea. We turn those in mathematical requirements, and then the mathematical requirements will give us a mathematical structure, and we can say that that mathematical structure is physical because it's justified by the physical requirements. So it's not that we are guaranteed that the object that we're going to have are not some mathematical construct that have no clear relationship to the physics. And this essentially solves all the problems that you might have of interpretation and all of that, because you start with the physical model. You don't start with the math and then you wonder what the math means. You start with the physical model. So at every point, you know what it is that you're describing. And the goal of physical mathematics is really to be able to look at any mathematical proof and read it, translate it in physics, so that every proof can be understood as some type of procedure, as some type of argument on the physical objects that you're modeling. And I hope to convince you that it's kind of transformative once you start doing things that way, because you don't have this mismatch between the math and physics that we currently have. Okay, so before we start, let's talk about what I call the fundamental misunderstanding in the foundation of physics, which is essentially the relationship between math and physics. The prevalent attitude among physicists, and it was also my attitude when I was out of university, because that's basically what you're taught, is that basically math is just a tool for calculation. And the technical details are better left to the mathematician, because there is no physics inside those technical details. It's just math. And Sabine Hossenfelder, in his Lost at Math, even though she criticizes the use of math in physics, sort of shows that she has this perspective as well. She says, but we don't develop theories by writing down assumptions and then derive observable consequences in a sequence of theorems or proofs. In physics, theorems almost always start out as a loose patchwork of ideas, and clean up the mess that physicists generate in theory development, finding a neat set of assumptions from which the whole theory can be derived, is often left to our colleagues in mathematical physics, a branch of mathematics and not physics. And in her mind, and in my mind 10 years ago, this is perfectly fine and logical, and this is how it should be. And even the ones in physics that work more towards the math have this attitude, and then have this idea that you have to start using this mathematical structure that a mathematician give you because they're better, they're more precise, and so on. Like, there is a fundamental problem with this, is that we don't just use mathematics to calculate. We use mathematics to specify our models. And specifying the models is the whole point of physics. This is called, in math, mathematicians call this mathematical modeling. And they're perfectly aware that the mathematical modeling should be done by the people in the respective field, not by the mathematicians. Mathematicians create the tools, And then it's up to the people in the field understanding what the tools are, how should they be used, and how should they be applied to their respective field. And one of the fundamental problems is that there is no single way to clean up the mess, because once I give you a patchwork of ideas, you have to clean up using axioms and definitions that are precise, and each axiom and definition represents a choice in the mathematical model, which means a choice in the physics that you're going to be describing. And since there are many of these choices, mathematicians don't know the physics, so they can't tell you what is the correct choice to make. And this is something that mathematicians told me. Like, they convinced me that this is how it works and it has to work. So we have this fundamental misconception in physics of how math should be handled. And so we end up with the wrong math. It's math that mathematicians develop for their own purposes because it's convenient for them to prove theorems or to make calculation, but it's not the correct thing to do the mathematical model. And so before talking about physical mathematics, let's go through just a couple of examples of unphysical mathematics that we use, but it's not quite the right mathematics to describe the thing that we would like to describe in physics. So, for example, in differential geometry, if you study differential geometry in a math textbooks right now, not from 100 years ago, you have this notion of tangent spaces and tangent vectors. And the tangent vectors are essentially defined as derivations. So a vector is a map that takes a smooth function and gives you back a smooth function, and it has some properties such that that map is actually taking the derivative along a particular direction. And in differential geometry, you use the partial derivative in every direction as a basis, and then you have components and you put those bases together such that you create the derivative in a particular direction. So now you can take this vector, give a function, and of course, this vector applied the function will give you a different function. And this is very useful to mathematicians because it gives an algebraic feel to this tangent space, and you can do some neat tricks. But the issue is this doesn't work for us because we have units. So how would this work, let's say, in polar coordinate? Well, we have a derivative in R and a derivative along theta. And these are the two elements of the vector spaces, either the basis for our polar coordinates, but we can't sum them because this would be an inverse meter and this would be an inverse radiant, and we can't sum them. They don't form a vector space because we can't sum them. Same thing in phase space. You have a partial derivative with respect to position, a partial derivative with respect to momentum. These are incommensurable quantities. Like it's not even like here that you can kind of fudge it because you put some constant so that you make this a distance. No, here you can't because these are completely incommensurable things. So this doesn't work. And this is the first sort of lesson that you have here, that if something is mathematically precise, doesn't mean that it's physically precise. And even if you can make some sort of translation because you say, okay, yeah, well, but some of the physical objects that we are studying are actually isomorphic to this, and so you can make a map and so on. The problem of having all these steps in between make the math farther for the physics. And so every time you have to translate back and forth, and it creates sort of a cognitive load that you don't even realize that you have. And it's only after you remove that cognitive load and you start having definitions that actually map, you realize why I was doing it. Everything becomes a lot simpler. So this is something that, again, it's how we do differential geometry, and it's something that differential geometry is something that we use in physics a lot. And the reason why I was able to sort of decipher the action principle and lots of other things is because I said, wait a minute, let's fix this. Let's make something that is closer to the physics. And once I started doing that, then the physics intuition kicks in and you start having conjectures, and then you can go back to the math and prove the conjectures and define things. So this is one example of physical mathematics. We need something like that. We need differential geometry, differential topology, but we need it with definitions that make sense to physics and then map well to the physics. And the mathematicians are not going to give them to us. We have to make them ourselves. Another issue is in quantum mechanics. In quantum mechanics, states are represented by a square integral function, complex square integral function. So, for example, this function here is a part of our Hilbert space, and it will give us a Gaussian distribution in position, and we can see that it integrates to 1, so it's normalized, and the expectation of the variance is 1/2. Also, this, it's still a sort of a bell-shaped curve, but the tails are fatter, right? This square root of 1 over pi y squared plus y. Also, this is a square integral function. So in principle, this is in our quantum state, and it integrates to 1. But you can see that the variance is infinite. And you should start thinking, well, do I really want variances that are infinite? And would these things make sense? And there is a problem with Hilbert spaces, because in Hilbert spaces, there is a theorem that tells you that every continuous linear operator defined on the whole Hilbert space is bounded. Therefore, any quantity, any observable that is not bounded, like position, momentum, energy, number of particles, cannot be defined on the whole Hilbert space, meaning that either the quantity sort of does not converge, like it's infinite, or it's not even well defined. Like it would be, say, one of those things where things keeps oscillating between positive and negative, and nothing converges. And so those objects are in the Hilbert space. And you could say, yeah, well, like any physicist does, we can just ignore them. Just take them out, and who cares? The issue is that you can create a coordinate transformation such that for one observer, the expectation is finite, and for another observer, the expectation is infinite. And that would mean that you are throwing out the states that are different from the ones that I'm throwing out. And that does not satisfy the principle of relativity. It just doesn't work. Even worse, in principle, you can have unitary evolution, therefore unitary time evolution, that move a state with finite expectation to one with infinite expectation. And again, these are clearly not physical. Now, these things don't happen in classical mechanics, because what you can do in classical mechanics is say, if I have a probability distribution, I can always cut it both in position and momentum. Like I can put a cutoff, and then my distribution has compact support. And if the distribution has compact support, I'm sure that all the expectation of all possible functions are going to be finite, because the maximum, and there's a maximum and a minimum for that function, so you're always good. In quantum mechanics, you can't do it, because if you take a wave function in position and you apply a cutoff, well, now you have a function that has compact support in position, and the Fourier transform of something that has compact support has not compact support. It's an entire function and spans the whole thing. So this is actually a problem, and which means that we probably don't have the right function spaces. There might be other function spaces where, like the Schwartz function, that would guarantee that all polynomial position and momentum are finite. But we physicists have to understand what are the requirements that we need to put on states, such that we can say, yes, we have valid states. So this is a situation that we have in the current state of the art. We have the physical world, which is our informal system of the things that we actually produce in the lab, right? They're well-defined physical objects because we can prepare, manipulate them, and so on. And then we have their mathematical representation, and we want to map these objects to these objects. Unfortunately, what sometimes happens is that we have objects that are well-defined, and we map to things that are not well-defined in the math, or we start with something that is well-defined in the math, we do some transformation, we get something that is not well-defined, and then we go back, and then we can't go back, right? And this is the current state of the art in theoretical physics. And I personally think that this is insane. Like we shouldn't have this. What we should have is this. We should have the physical world with a set of things that are well defined, and then we have the mathematical representation, and we can go back and forth, and we know exactly where the limit of the mathematical representation and where the limit of the physical world in terms of the assumption that we're using, and we can go back and forth. And if you start doing that, you realize something, that since you have a set here, you're defining what are the conditions of the physical systems to have the mathematical representation. And then you have the set of mathematical objects. So you have two definitions here. You have physical specification and mathematical definition. What needs to happen for you to be able to make this nice map is that the physical specification has to be equivalent at the mathematical definition. So instead of mapping the object one by one, you're taking the physical specification, mapping it to a mathematical definition, and that's exactly the case in which we can make this map. So what we're going to say is that a mathematical definition is physical if you can do this, if it captures and only captures an aspect of the physical system. And ideally, we would like all the mathematical definition that we use in physics to have this property. And if you can't do it, then you need to fix it. And as I was saying before, you can only do this if you start at the lowest level of the system, of the mathematical structure. And most of physicists don't even know what are the lowest level of this mathematical structure. We're going to talk about topologies here. I don't know how many people that come, that are here, that come from a physics background know exactly what a topology is. But that's kind of part of the problem, is that there is this idea that one can do foundations of physics without having absolutely no clue on the foundations of mathematics. And it just doesn't work like that. Okay, so one of the things that we have to understand is how to do it, right? How can we are able to map, how should this standard of rigor go from physics? Like, mathematicians have developed their standard of rigor for their discipline, but as we saw in physics, you sort of, oh yeah, you make a mess. We don't have standards of rigor. But if we want to do physical mathematics and we want to do it properly, we need a standard of rigor. And we need to define it ourselves as physicists, make something that makes sense to us, but then also gives to the mathematician something that makes sense to them. Otherwise, we're not really doing mathematics. We're doing physical mumbo jumbo. Okay, so how should we do this? And this is the setup that we have come up with. Again, it might not be the perfect standard, but it's what we have. And right now, with it's better. It's definitely better than what we have. So, for example, let's say that we want to define an axiom, and we want to define an axiom on a space of ensembles. And if you're a physicist or an engineer, you know what an ensemble is. It's part of the statistical description of a system. And one of the things that you want to say that if you have two ensembles, you can make a statistical mixture, and the statistical mixture is yet another ensemble, right? So that you can always take two ensembles, make a statistical mixture. We have given probability, you're always going to get another ensemble. And this, again, if you study statistical mechanics, if you know what probability distributions are in the conception lab, this is an informal intuitive sense. It's something that that makes sense to any physicist and an engineer. It's you don't need to explain to an engineer or a physicist that a statistical mixture of ensemble is an ensemble, right? But if you give this to a mathematician, they're going to tell you, I don't know what ensemble is. It's not precise. It's not this is what mathematicians are going to tell you. It's not precise. It's not precise. Okay. So you say, okay, mathematician, formally, an ensemble space is equipped with an operation plus that takes a number from 0 to 1, two elements of the ensembles, and gives you back another ensemble. And it's called mixing. And we note it with an infixed notation. And it has this following property. So now we have a formal requirement that the mathematician is going to say, now this feels precise. But of course, the physicist is going to say, okay, what is all these funny symbols? Why do we have them? And so we need to close the loop. And how do we close the loop? We need a formal justification, something that shows that the formal, informal, intuitive requirement justifies the use of this formal requirement. So it's kind of like a proof, and to a physicist, this might feel like a proof. And maybe if we went back in time in the 1700s, even mathematicians would have considered it a proof back then. But it's not a proof right now, because it's not all within the formal system. It takes elements of the informal system to justify things that you're putting in the formal system. So let's go through all of it, so that you can see how it works and you can see the level of precision that you can get. So this axiom captures the ability to create a mixture merely by selecting between the output of different processes. So now we have a clear idea of what is being modeled. We have the two processes, and we are creating a process out of those two processes. So let E1 and E2 be two ensembles that represent the output of two different processes, P1 and P2. Here's P1, here's P2, and here's the output. Let SP be a process that outputs two symbols, the first with probability P and the second with probability P bar. Then we can create another process P that, depending on the selectors, output either the output of P or P2. All possible preparation of such a procedure will form an ensemble, because that's what an ensemble is the collection of the infinite collection of all the possible outputs of a procedure. Therefore, we're justified in equipping an ensemble space with a mixing operation that takes a real number from 0 to 1, the probability of the mixture, and two ensembles, E1 and E2. Okay, so now we have a clear idea of what it is that this plus thing is describing, because we know what it is as a model. Now we need to justify all these different properties. So we say that it's continuous. Then we say that given that mixing represents an experimental relationship, and all experimental relationship must be continuous in the natural topology, mixing must be continuous. Note that P is a continuously ordered quantity where no value is perfectly experimentally verifiable, and therefore the natural topology is the one of the real. This justifies continuity. Now, of course, you haven't seen all the previous parts that we have, but that's kind of the point. This is the point that I was saying before. If you want to have everything fully justified, you have to do it from the most basic structure. So we're going to have some justification from previous finding that if you have experimental verifiability, you have topologies, and experimental relationships have to be topologically continuous. And so we can use the previous result to justify our axioms. Okay, now we have to justify all of this. If P equals 1, the output of P will always be the output of P1. This justifies the identity property. In fact, the identity property says that 1A plus 0B gives you A, right? If P1 and P2 are the same process, then the output of P will always be the output of P1. This justifies the idempotent properties, right? So, and the idempotent property is PA plus P bar A equals A, which is exactly what's happening here. The order in which the processes are given does not matter as long as the same probability is matched to the same process. The process P is identical under permutation of P1 and P2, so we have commutativity. And if we're mixing processes P1, P2, and P3, as long as the final probability are the same, it does not matter if we mix P1 and P2 first or P2 and P3. And this justifies associativity. So there is the issue that you have sort of to take these and, oh, by the way, I didn't say that P bar means just 1 minus P. You have a lot of 1 minus, and it's just easier to put a bar on top. But then the issue is that now you have to prove that these numbers here, when you do the multiplication, are the same, and you can actually do it with just a little bit of algebra. And so this is the kind of thing that I think we need. And the thing is that it's totally possible and doable. So at this point, there is no question as to what the math describes. We don't have a problem of interpretation or stuff like that. The properties are justified by and are a consequence of what the model describes. So if we are describing that, you must have those properties. There is no way around it. And then the idea is that then every math proof can be understood through this description. So if you have 10 pages of math proof, in principle, every step that you have, you can go and say, okay, there is a process, I'm doing this, I'm doing that, and so on. And so the whole point is that the math now describes and only describes a physically meaningful concept. It's physical mathematics. It's mathematics that is representing something physical. And it's clear what is going on. Okay, so the goal of physical mathematics is essentially to record all of the mathematical structures that are used in physics in this way. It's a lot of detail, right? And it's a lot of bumping your head against the wall and trying to figure out what are the correct sampling points and why do we have them. But once you're doing that, you have a clear realm of applicability of each mathematical structure. So you know why do you have that linearity, right? That linearity that we had in that space was coming from this idea of mixing. And in fact, one can see that all the linear structure in physics actually are inherited from the linearity that we just seen of the mixing of statistical structures. So you really know where things come from. You get this perfect map between math and physics, and you can go and provide generalization for structures for all physics, because the fact that an ensemble, a statistical mixture of ensemble is still an ensemble, that applies to all of physics. It doesn't matter if you have a classical space, a quantum space, a quantum field theory, or even a theory that of quantum gravity that we don't know what it is. We know already that there's going to be some linear structure in that theory, because when we take statistical mixtures, we need to be able to have a linear structure there. So to me, this is just a better way to do physics. And you have to get used to it, because it's very different from what we currently do, where you just, oh yeah, let's try to use the group G24 and see what happens. It's a lot more details, and you need to be cognizant of a lot of nuts and bolts of how the math work, because you have to sort of select what are the correct nuts and bolts. But it forces you to think a lot deeper about physics. What it means to have an experimentally based theory, what it means to have defined states, what the entropy is, what the energy is. And then suddenly, all these details become meaningful. There is no just a math thing. The topology is meaningful. The way that you make limits is meaningful. The convergence criteria is meaningful because it's connected to the experimental variability and so on. And so you get all these details, and you get this. Yes, it becomes a lot easier to have a better intuition in both the math and the physics. So these are the takeaway from this section is, first of all, is that it is possible to define starting points for physical theory so that they're both mathematically precise and physically meaningful and philosophically consistent. And this is the first surprise, because if you told me 10, 15 years ago that you could do that, I would have probably objected. And if you probably told me that I was going to do it, I would say you're crazy. Because you're trained for a long time to think that, math, physics is always going to be hodgepodge. And in some sense, it is true. But you just have to do it correctly. There is a way to do it, and a way that it works. And so this is the first part, you can do it. And so physical mathematics, the goal is to find mathematical structures that are justified by the physics, and this justification provides a new standard of rigor for physical theory. It's something that we currently do not have, and I really think that we do, especially if we want to extend physical theories to regimes that are not regimes in which currently physical theory work, because you don't know whether the math is going to work. And as I said, mathematics has gone to a more abstract path, which is totally proper for mathematics, but then it's going to bring in some things that are not going to be useful, not going to be physical for us. So only mathematical structures that are justified by unavoidable physical requirements can serve as a truly foundational structure. So this is where you see really the difference between the foundation, like the foundational objects as they're normally perceived in physics as, the fundamental constituents and the fundamental forces, the one for which everything else is an approximation. No, for us are the unavoidable requirements that are there in every physical theory. As I said, every physical theory is going to have ensembles because we need the statistical properties, because those are the ones that we actually go and measure and validate experimentally. And so all physical theory must satisfy those requirements. And so now these requirements can form that theory of the physical model, because now all models must at least give you that structure. And so again, the whole perspective here is that the foundation of physics is not just guessing what the physical world is made of, but articulating in a precise way what physical theory are and what are the things that we do, that we must do when we do physics. And this brings the foundation of the physics, where frankly, a lot more in line to what the foundations of math and the foundations of computer science are, both conceptually, like in math, you want to understand what is math, what is a proof, and so on. In computer science, you want to understand what is computation, what things can be computed and what not, what are the classes of computations. We're going to want to be able to do the same thing in physical theory. Well, what is a physical system? What does it mean for things to be experimentally connected to experimental verifiability and so on? But it also brings it more closest in terms of the mathematical techniques that you have to use. As we're going to see, it brings in a lot more lower level logic part of things, order theory type structure, which are actually closer to what those other fields use. So it's all very interesting. Okay, so what we're going to do right now is actually see an example of a fully fleshed theory and a connection of experimental verifiability and topology sigma, which I talked a lot. So let's go and look at it at least briefly. So we want to start with principle, with ideas that basically tells us what is it that we're doing. And so we start with this principle of scientific objectivity that tells us the science is universal, non-contradictory, and evidence-based. So this means that science is about statements that are associated to experimental tests. So we have a statement, and it can be true or false, but then the statement is associated to an experimental test. And the experimental test is tricky because it can succeed in finite time, it can fail in finite time, or it could also be undefined. Like it could be something where you have no end. So for example, if I wanted to ask whether there is extraterrestrial life, I can start looking for extraterrestrial life. And if I find extraterrestrial life, I'm done. I found it. But if I don't find it, I can't terminate and says, oh, it doesn't exist. There is no termination condition. You have to keep going, keep going, keep going. And you can assume that, if there is, at some point, you're going to be able to find it. So you can assume that the statement is verifiable. If it's true, at some point, your test is going to succeed. But you might not be able to assume that it's also a falsifiable statement. That is, that if the statement is false, then the test is going to succeed, is going to fail in finite time. And so what we're going to do right now for the next 15 minutes is just understanding what this simple thing gives you in terms of a mathematical structure. And that's it. So again, one of the key elements that we also saw yesterday, it's finding simple ideas that seem trivial, but that have a very large set of consequences, and in particular here, they give you a rich mathematical structure. So if you look at the book, this whole idea is characterized in two sets of axioms. The first two axioms are what I call the axioms of logic. It basically tells you that there are statements and you have a logical context, and formally a logical context is just a set and the statements are just elements of that set. And you have a truth function, something that tells you this statement is true, this statement is false. So there exists a truth, and this is what makes science objective, that there is a truth and there is only one truth for everybody. Then you're going to have possible assignment, like you don't know what is the truth, but you know that there are some constraints. So for example, if I say that that animal is a cat, I know that it's not going to be a dog. And so if I assign false to one, I can assign true to one, I have to assign false to the other. So not all statements can be assigned any truth value because the statements have meaning, and the meaning prevents particular assignment. So we're not going to define meaning in terms of the mathematical structure because it would be too complicated. And so one of the thing that you have to do in physical mathematics is realize what makes sense to put in mathematical structure and what to leave out, and just leave it in terms of justification because it's more convenient. And then design the axioms such that they are easy to justify. So the axiom that we have here, like these three axioms, are going to be equivalent to say that you have a Boolean algebra, which is what you would define if you were doing logic mathematics, you basically just say, I have a Boolean algebra. The point is that justifying all the properties of Boolean algebra becomes cumbersome, becomes not really intuitive physically. Instead, justifying this set of axioms becomes a lot more intuitive, and you can do it much more easily. And so that's why we have this idiosyncratic way of defining a Boolean algebra and the things that we have. And then we're going to have, we add the structure of verifiability without adding the test, because again, the tests are cumbersome, and you can't really fully formalize what a test is and how it works, because a test, at the end of the day, it's something that exists in the real world, and it has very, very many complicated features. So you just assume that there are some verifiable statements, so some statements that if they're true, eventually you're going to be able to say, yes, they're true with a test. And you're going to have now some properties of these verifiable statements that you can justify. And so let's, for example, take one of these axioms, the axiom of verifiability, that tells you that a verifiable statement is a statement that, if true, can be shown to be so experimentally. And again, this is the informal part. And now we have the formal part that tells us that each logical context contains a statement, and the statement, a set of statements that is a subset of the verifiable state of the full context, and those elements are said to be verifiable. So we're just declaring that there are some of these are verifiable. And then you know that every certainty is verifiable. A certainty is something that it's always true in every assignment. Every impossibility is verifiable as something that is always false in every assignment. And a statement equivalent to a verifiable statement is verifiable, because conceptually, these two statements are equivalent if they're always true or false at the same time. So if I have a test for one, then of course I can use that same test for the other case, right? And so this is the structure that you have. You have the context with all your statements. You have a subset, right? And this is in the formal part. And this, in the informal system, you have these experimental tests, which we're going to use in the justifications, but you don't use them in the formal side because it would be too cumbersome. You wouldn't be able to make really a good theory, and they're not necessary. So the fact that you can get away with it also tells you that they're not really so important. The important thing is that you can say that some elements are verifiable and some aren't. Then you're going to have another axiom that tells you that the finite conjunction is verifiable. So if you have finitely many statements and you have an end, a logical end, you can verify the logical end just by testing all the tests one at a time, right? So this is the procedure. You run all the AI. If they all succeed, they're all going to succeed in the finite time. Therefore, you're going to be able to reach step 2. And then you're going to return success. And if they didn't, if one of them failed, then you go and return failure. So you can write a pseudo code, a pseudo test to be able to show that you can, in principle, always do that. Now, for the OR, the structure is a little bit different, because if you have the disjunction, the OR, as long as one test terminates in finite time correctly, like if it succeeds, then you don't need to test all the others. You can disregard them and you just can return success. The only problem that you have to be careful is some of these tests might not terminate. And so you have to have a procedure that explores all tests for an arbitrary large amount of time. And so what you can do is that you initialize n to 1. So now you run the first test for 1 second, and if you succeed, you quit. Then if you don't succeed, you increase n and you go to 2. So now you're going to test the first 2 statements for 2 seconds, and if you succeed, you finish. If you don't, you go back to 1 and you increase, and so on. You keep looping. You're looping. At some point, this procedure is going to test all your statements for an arbitrary large amount of time, and of course you're going to find it, right? So it still feels like a proof, but it's not a proof because we haven't defined what these tests are and what a procedure is and so on. So it remains part of the justification. But the important thing is that you can only do a countable collection, because if the collection is uncountable, you can't find the test that terminates. So it still feels very mathsy, right? But it's a justification of their axiom. And these are the type of things that you also have in intuitionist logic, where you have similar type of axiom structure, because that's the type of logic that what we are doing. So what you can do at that point, you can say, okay, now I have a set of statements, and I can say that these statements, D is generated by a basis, by a set of statements. If I can reach every statement in D by this finite conjunction and countable disjunction. So that basically, I only know how to test B, right? I have the test defined on B, but now all the verifiable states in D can be constructed from the tests of B. So everything is explorable just by exploring the basis. And so you define experimental domain as a set D that is generated by a countable basis, because that's what you can test. If I even give you an infinite amount of time, right, an arbitrarily large amount of time, which is not infinite, an arbitrarily large amount of time, you can only create a procedure that can explore countably many. And so that's the most that we can explore experimentally. And so now we know that every sort of realm that we can go and experimentally explore has to be one of these things. There's a set of verifiable statements that have a countable basis. From this, then, you can generate a theoretical domain, which includes all the statements that have the test, regardless of termination. So this does not add the new information. It just adds new statements that are still well-defined physically, because they have an associated test. And then you can define a possibility as essentially something that tells you what would be the statement, the truthfulness or falsehood of all the statement, if we knew that that possibility were true. So, for example, if you have the set of all possible measurement of mass, right, and the verifiable statements would be the mass of the electron is greater than I don't know, than 0, but less than 1 electron volt, right? That would be a verifiable statement. And if I knew that the mass of the electron were precisely one number, I could tell you what all the verifiable statement would be true or false, because I would just see whether the actual value, the true value, is within that range. And so the possibility basically is that it's the mass of the electron is exactly this number with infinite precision. And it turns out that these are actually statements within the theoretical domain. And so you end up with this correspondence. You have your verifiable statements here. You have the theoretical domain, which is all the things that have a test. The possibilities, which are the experimentally defined case. So the mass is 1, the mass is 2, and so on. And what you can show is that there is an isomorphism between this and topological spaces. The points correspond to the experimentally well-defined cases, like all the possible values of math. The open sets represent the verifiable statements, so the things that are connected to experimental verification. And what are called the Borel set now represent all the theoretical statements, the things to which you can associate tests. And then you have this perfect math. If you have a statement, the statement can be understood as a set of possible cases where that statement is true. The interior, topological interior of that represents where the test would succeed. The exterior would represent where the test fails, and the boundary, the topological boundary, represents the part that remains undecidable. And an open set is a verifiable statement. So if you have a range of mass, you can say the mass of the electron is within that range. A closed set, like at a single point, the mass of the electron is exactly 510 kilo-electron volt. That's not a verifiable statement, but it's a falsifiable statement, because if I verify that I have a range that excludes that, then I can do it. And then there are other Borel sets, like the set of all the rationals, right? This corresponds to the mass of the electron in kilo-electron volt is a rational number. This is, in principle, it's a statement that makes sense, but it's undecidable. And you can see that it's undecidable physically, because you're never going to settle this, because you would need infinite precision, and you're never going to get infinite precision. In topologica, you can see it because this set has no interior and no exterior. It's basically all, the boundary is the full space, which means it's an undecidable statement, because the corresponding test is never going to terminate. So you can make this map, again, precise, and then you can get notions of limits and all of this. But the thing is that you can, with just this simple idea, you can make sort of very broad, you can find very broad consequences. So if the set of distinguishable case E comes from countable limiting tests, then each point can be represented as a string of false and trues, and which also means a string of zeros and ones, but a countable sequence of 0 and 1 can be understood as a binary expansion of a real number between 0 and 1. Therefore, the set, the cardinality of the possible cases that we can distinguish experimentally cannot be greater than the set of the real numbers, which means issues about higher infinities, large cardinals and stuff like that you have in set theory, you're going to say, well, we're never going to care about that. And probably intuitively you would have said that, but now we know why. Like, there is a reason why we don't care about cardinality greater than the continuum. And things like the set of all these continuous functions from R to R have cardinality greater than the continuum, and therefore they cannot represent physical objects. And again, this would be intuitive to a physicist, but there is an actual reason. Like, it's not that, oh, you know, there is a Hodge, no, there is a precise reason as why that's the case. Another thing that this justifies is we really have a physical understanding of what the Borel sets are the set that have associated with tests. And so when we create probabilities and measures, we have to use those sets because those are the ones that are physically meaningful. And this essentially tells us why we don't have problems like the Banach-Tarski's paradox that there is in math, and physics is sort of protected by that because we don't use all the sets. So if you don't know what the Banach-Tarski paradox is the idea that you can get a set of, you can get a ball and divide it into at least 5 parts. You recompose those pieces into 2 balls of the same size by doing a transformation that in principle preserves the sizes, right? And this is basically tell you that it's basically impossible to define a measure on all the possible subset of Rn. And again, these problems are avoided because, well, all those sets that are non-Borel sets are not physically meaningful. And therefore, we don't have to talk about them because they're not physically meaningful. And therefore, we solve these problems. So again, this is where knowing the foundation of a little bit of foundations of mathematics is useful to understand what needs to happen in physics, but also the reverse, right? This physical mathematics can give us insight into these foundational issues of mathematics, at least, you know, how they're solved for physical theories. Another thing, we start running out of time, so I have to be quick. Another thing that you can find is that the causal relationship you have, if you have mapped between these spaces, they have to be topologically continuous maps. But topologically continuous map does not mean analytically continuous map, because again, the topology is defined by what we can measure and what we can verify. So, for example, we can verify that we are at a triple point if we have an equilibrium of the 3 phases of liquid, vapor, and solid. But we don't do that by measuring pressure and temperature. We do it in a completely different way. We have a different way to verify. And then we can say, okay, we are here. And now that means that that region, any phase transition that it's a region of phase transition becomes topologically separate, because you can say, oh, I am on this line, no, I am on this point, and so on. You have a different way to verify that you're actually on this line, on this point. And if you have, you can have now analytical discontinuity over phase transitions without breaking topological continuity. So the idea is that really this definition works very well even at these extreme cases, and again, they give you even insight of why you know, you would choose the triple point as a starting point of defining temperature and so on. So again, the main takeaway here is that requiring experimental verifiability in a physical theory leads to a topology as a sigma algebra. Every set of distinguishable cases or physically well-defined cases is a T0 second countable topological space. And open sets correspond to verifiable statement, continuous function preserve experimental verifiability, and Borel sets correspond to statement associated with tests. All the proofs can be understood now as describing argument on experimental verifiability. So limits are defined on top of the topology. Then you're going to have a truth sequence of verifiable statements that become a constant. That's what a limit is. Right? At some point, I say, yeah, that thing is true because it keeps being true and it will always be true. A topological distinguishability, the separated axioms become experimental distinguishability. How well I can distinguish two statements and say that if one is true, the other one is false. And as we saw, the interior, the exterior, and the boundary become the verifiable, falsifiable, and undecidable fact. So the point is that once you have a good understanding of what the foundations are, then it's easier to understand why the constructions that are on top have to be done in a particular way. So probability measure in general measure theory are defined on the sigma algebra, on the Borel algebra, because we assign probabilities and sizes to statements with tests, right? So if you can't, this also tells you, like, if you for people that are talking about hidden variables, right? How you are going to assign probability to hidden variables if you don't have a set of experimental tests that you can associate them with? What are those probability actually meaning? It's not what we mean in physics, that's for sure. Or you can also have the notion of topological groups. Then these are groups of transformation, usually groups of transformation, that we can experimentally define and identify. That's why in physics, if we have a group, it's going to be a topological group because the elements have to be experimentally verifiable. You need to be able to know what transformation you have. So again, the main takeaway should be that it is possible to develop a foundation of physics that is both mathematically rigorous and physically meaningful. That we are able to make this map. We're going to be able to say, yes, we have statements that have tests, and then we define, we correspond them here. We have all our axioms, and then we can find topologies and sigma algebra in a precise way. And again, no issue of interpretation, and you know when the tools of mathematics are applied and if they're applied correctly. And it should be clear, hopefully by now, that there is no just math. That thing just has to go from your head if you have it. There is nothing that is just math. Either the math that we're using in physics represents physical objects, then it's describing physics, and it's not just math, or it doesn't. And the theory should be stripped away from the physical theory because it's just cumbersome stuff that shouldn't be there in the first place. And only by understanding the full details of the math and the physics, you can make that determination. So you can't just say, oh, it's just it's the job of the mathematician, because it doesn't have the physics part. And if you're a physicist and you want to do this, you have to become at least knowledgeable enough to be able to talk to experts such that you can make the translation and understand what you need and what you don't. And unfortunately, a lot of people that work on a foundation do not know these issues in the foundation of math. And so if you do not know what the well-ordering of the reals is, right, you are precisely the person that cannot determine whether it's physically significant or not. So if somebody says there is just, this is just math, and doesn't know exactly what the math is, he's really the person that can't not make that value judgment. Okay, so wrapping it up, assumptions of physics, it's a different approach to the foundations of physics. Again, there are no interpretation, no theory of everything. We just have a physically meaningful starting point from which we can derive the laws and the mathematical frameworks. And physical theories are just models, and therefore we just need to be clear of what that model is describing and what is the realm of probability and so on. And physical mathematics wants to do this very precisely, such that we can derive the math required from the physical requirement, from the physical models that we have in our head. And in physics, mathematics is used to make to model physical system, and therefore we need the mathematics that is designed specifically for that purpose. Issues of large cardinals and all the hierarchy of infinity is fun, but it's clearly just math. That is just math. It's not going to be useful to define a physical system, and we need to understand what parts of math are useful or not. And again, you need to start at the lowest level of mathematics, because rigor, precision, meaning, correctness cannot be sprinkled on top. So if you don't know the foundational layer, you don't know what the top layer is. And I'll leave you with this Gall's law. Big system that works evolve from a small system that works. They never come from big systems that do not work. So the only way to do this is to retreat to the smallest thing, understand the smallest thing, and then making a little bit bigger by keeping this full understanding. I have no idea how long it's going to take, but this is the only way to do it. And I think I am done.
All right. We've got a few questions in Q&A already. So Leandro asks, what are your thoughts on Nivaldo Limos's reply to your paper in his article, Are Hilbert Spaces Unphysical? Hardly My Dear, which appeared on Foundations of Physics in the end of May. He asserts that your pivotal charge against Hilbert spaces is that by a change of variables, which is a change of basis unitary transformation, one, quote, can map states with finite expectation values to those with infinite ones. In the present work, it is shown that this statement is incorrect and the source of the error is spotted.
Yeah, we are preparing a one-page reply. Actually, a person in a student that is following the project is actually spearheading that effort, because I didn't have the time. The response is quite simple. So he claims that a coordinate transformation is just a change of basis, and therefore it does not change expectations of the variables. And this is clearly false. If I do a translation, the value position better change, because if it remains the same, I have done nothing. The problem is that in the transformation, he both changes the state and the system. Like in a coordinate transformation, you can make an active transformation where you change the system but leave the variable the same, or you can do a passive transformation. You keep the system the same, and you change the variables that you're using to describe the system. He changes both. Of course, if you change both, nothing happens, but that's not a coordinate transformation. It's the thing that is staggering to me is that he contacted me and I told him this point, like, this is how coordinate transformation work. It's not something that I made up. If every, even when you do classical mechanics, it's like that. When you do, coordinate transformation on a manifold, that's what you're doing. You are changing the local chart. And the fact that it was published in a journal is very surprising to me, because again, it's undergrad stuff. So yeah, so we are preparing a response, and as I said, to me, the thing is so trivial that I didn't want to waste time with it. I just wanted to do other things, and then I said, basically, in our Discord, if there is somebody that that wants to write this, and I tell you what you basically need to find, you're gonna be author, and we respond to this. And one person, Robbie, decided to take this up. He brought up an excellent first draft, and he found a textbook that basically just says that, and we're gonna respond for a letter soon, I think. So that's how it works. And again, it's very disappointing that this is the level of conversation on the physics journal on the foundations. And I'll make a video at some point about this thing specifically. Like the purpose of journals should be to sort of make the discussion proceed by sort of, okay, this is something that has been already settled like 20 years ago. We're still in the foundations of physics, foundation of quantum mechanics specifically, talking about coordinate transformation. As if this is not has been settled like, I don't know, 100 years ago. I don't know, I find this. I don't have a word even. So.
Next question is in fact from Robbie. In quantum mechanics, could it be that Hilbert space is the correct space for physical states, and that there's something unphysical about the operators that are not defined on the whole space? If we could modify the position operators that it is defined on the whole Hilbert space, wouldn't that fix the problems with expectation values?
Well, that's where you have to define what a state is, because most of the time the state is defined in terms of measurable quantities. So if your measurable quantities are not well defined, then neither is the state. You know, that's the whole thing. Yeah, that's it. So to me is either you have a different way to identify the state that is not through the measurable quantity, like in the example of the triple point, right? You identify the triple point not because you're measuring the pressure and the vol and the temperature, and you say, oh yeah, I'm at the triple point. No, you verify the triple point because you're verifying that you are at an equilibrium of the three different phases. So if there are different ways that are not the statistical measurements to identify the state, then sure. But in quantum mechanics specifically, I don't see anything else, especially on the continuum.
I think since it's a little bit more related to a question in the chat from Luther, the direct delta function isn't a physical object? Just with regards to
again, it's definitely not a state because it would mean that you have so the delta function in quantum mechanics is problematic. It's very problematic because it's you know, we talk about a uniform distribution in momentum when you have a delta Dirac in position, as if that's something that is sort of probabilistically well defined, and it's not. This is something that, again, when I started working on this project seriously, I started basically auditing a lot of math classes to sort of be able to talk to mathematicians in a precise way. And you know, at that time, you know, I was used to thinking about, yes, uniform distributions on momentum, and then of course the professor starts talking about that these are like they don't exist. This is the problem of the mass escaping at infinity, because it's a known problem that it can't be solved in probability theory, essentially. And of course, he doesn't know quantum mechanics. He doesn't know that some people are saying these things. And I said, oh, okay, that really doesn't work. And this is kind of the same problem that I was having before. We were saying before, if you take a function that has a compact support, has a sort of an infinite spread in momentum, so that he has to get all of this. So yeah, as a state, it really does not. Again, it would mean that you would have an infinite energy, an infinite spread in momentum. It just does not make sense. It can be a convenient mathematical tool to you know, to do some things, but you have to understand that it's maybe the limit of something. And so, for example, delta Diracs are very, very useful when you do signal theory and control theory, because they have essentially it's like they have a component in every frequency, right? So if you have a system and it's a linear system and you want to characterize the frequency response of that system, what you do is you send an impulse, and then the output, right, is essentially the response of the system on all the frequency. So you take that output, you do a Fourier transform, and you basically have the frequency response of the system. So it's a really great thing. And then you're mathematically, you can get this result precisely. But of course, you're going to think of the delta Dirac as a limit of impulses that are shorter and shorter and shorter, right? And then you take the limit not as something that is true, you take it as a limit. When you're doing physical mathematics, it's very important that you understand what objects in the model you think are physical, and like they're things that in principle you're assuming that you can prepare, and the things that are actual limit, right? And you may take a space and you say, okay, this is the space, but for convenience mathematically, I add the limits and I do things on the limits. You can still do it as long as you are able to make that distinction. So you could even say, look, I start with a physical space, like that it's not going to be the Hilbert space, it's going to be smaller. And then I say, that's the physical thing, and I know what the physical things are. But then for convenience mathematically, I complete it in the inner product, and I get a Hilbert space. I do the mathematical calculation in the Hilbert space because it's more convenient, and then you get the result. As long as you're guaranteed that the result that you get of the final calculation is still on the set of objects that are physical. Right? It's a little bit like when you are doing complex analysis as a stand-in Fourier analysis. So you have an equation or an integral that you have to solve on the reals. On the reals is complicated. You pretend that the variable is complex. You make the integral, and then you go back to the real number, right? You can still do it. It's a mathematical trick. You can do it. But again, the problem here is not what am I doing during the calculation, is what I'm doing during the modeling. And I want to make sure that every element in the modeling makes sense, and all the steps in the modeling make sense. And then I can go and expand through calculation. And this is, I think the problem to me is that if you are not worried about a calculation, but you're worried about issues of interpretations and the meaning of the theory and so on, you should be working on the physically meaningful subset, not on the extended subset. And this is why we have a lot of problems, I think, in the foundation, that we can't make that distinction.
But Braz's question in the chat whether a participation certificate will be sent. We had not been planning to, but if that is helpful, we can do so. Wasn't sure if Ibras had to sign off, so I wanted to answer that right away. So I've made a note of that.
Yeah, only to the people that are actually live, and you can see that they were in
the Zoom. Yeah,
in the Zoom.
Yeah, YouTube we don't have any information about who's streaming it. Moving back to the Q&A, there's a question from Thomas. Has any work been done on the physical justification of Clifford or geometric algebra? What could physical mathematics have to say about vectors and more generally multivectors? So
I have, and we're going to see it tomorrow in the open problems, that I do have a starting point on what is a derivative, what is differentiability, and all that, and essentially forms and all of that, and how they can map. It needs to be closed, like it needs to become like a serious mathematical theory. Right now, it's a good thing for, let's say, again, for understanding what is it they're doing and having a nicer notation for doing the math, and so that we can understand what happens. I do not have a full, but what I have is going to be more similar to what differential topology has than what Clifford algebra have. The problem with Clifford algebra is that they basically put things with different dimensionality in the same space. So, conceptually, you can imagine that you have points, infinitesimal lines, there are vectors, infinitesimal surfaces, there are bivectors, infinitesimal volume, three vectors, and so on. What Clifford algebra do, at least what I understand that they do, is they put all of these together such that you can define a product that essentially takes, say, two lines, and it gives you both a point that represents the scalar product and a bivector that represents the area. And that's precisely what I don't want to have. I want always to be clear which are objects of the different dimensionality, because again, physically, you can't really sum lines with areas, like numerically, you can't sum them. What the Clifford algebra does is that they're not really summed. Like you're still in sort of the sum of those spaces. But then again, what is the topology that goes across these things? It becomes a very quirky. I think you can get a similar result that map better to the physics by using the notion of differential topology. And also my issue is that I need to take all these things and be sure that they work in infinite dimensional spaces. So the way that I'm defining these forms and so on are things that hopefully, and this is the part that needs to be checked more carefully, can generalize well to infinite dimensional spaces so that we can talk about, let's say, a metric tensor in quote in an infinite dimensional space, which is something that you really can't do, for example, in differential geometry because what's it called? You're finite dimensional. Manifolds are finite dimensional. That also, of course, opens a complete can of worm because there is no good theory or unique theory of Lie groups, let's say, on infinite dimensional spaces and so on. So there are like lots of problems on the math side. But again, this is where I think the physical mathematics should give us more constraints than the math has, such that we can actually find the good structure. So the short answer is there is going to be something that plays the role of differential topology, differential geometry, and Clifford algebra, but it's not going to be exactly that because, again, those mathematical definitions weren't thought with the idea of working in all the type of spaces that we need in physics.
All right, let's go ahead to Daryl's question. Can you explain why the countable disjunction can terminate in finite time?
Yes, so that's basically a trick. So imagine that you have a test. The whole idea that you have a test, it means that it's repeatable. It means that you can do it however many times you want. So if you have a test that it hasn't terminated in 5 minutes, you can always stop it and restart it later, right? That's basically it, because otherwise the test wouldn't be repeatable. You wouldn't be able to start again and again. Okay, so if I have now countably many statements, like let's start with finitely many statements, right? I need to be able to test, I need to be able to check. Let's say that I only have 2 statements. One of them will terminate in some finite amount of time, but the other one, let's say, that never terminates, okay? So what I can do is to test both of them for 1 minute. And if neither of them terminated, I can test them for 10 minutes, and then for an hour, then for 5 hours, and so on. At some point, the one that will terminate in finite time, and so will hit the finite time that is required for the test to terminate. And then since it's an or, right, it's A or B, as long as one of the two terminates correctly, then you know that the disjunction is true, and so you can terminate. Now, this works for 2, and with 5 you can also say I test 5 for 1 minute, for 2 minutes, and so on. The problem is that when you have countably many, you can't test countably many for 1 minute because it's already an infinite amount of time. So you first test the first for 1 minute, then they test the first 2 for 2 minutes, the first 3 for 2 minutes, the first 4 for 4 minutes, and so on. This is a diagonalization process. In the foundation of mathematics, a lot of the simple, like the thing is a fundamental level, the fact that, for example, that the reals are not countable and so on, you use this type of diagonalization. So it's a basically standard math technique. And so by basically saying I take the first one for 1 minute, the first 2 for 2 minutes, the first 3 for 2 minutes, and so on, you are testing all tests for an arbitrarily long time. So at some point, if there is one test that terminates in finite time, at some point you're going to test it, and you're going to test it sufficiently long, you're let the test run for sufficiently long that it will terminate. At that point, you're going to find that one test that terminates, all the other things, it's a disjunction, it's an or, as long as one thing terminates, the whole thing is true, and then you can quit. And the only requirement is that you have countably many. So if you had uncountably many, like the continuum, you wouldn't be able to have this sequence, so you wouldn't be able to find the the correct test. And what is interesting even here is that when you make a sigma algebra, right, the thing where you define a probability and you define measure for, and which I'm claiming this is an algebra of tests, the closure in terms of unions and intersection of sets, which corresponds to the ends and the or, because the union of the two sets is the or and the intersection is the end. It's required only on countable operation, which is exactly the type of operation that you're guaranteed to be able to make within algorithms. So all these things sort of map together too cleanly to basically say, oh, it's just a coincidence, right? This is what we are describing. So I hope it made it clear.
I have 4 open questions. I think we might be able to get through all of them, but might need to move a little bit quickly with relatively short answers. So Marwan Mohammed asks, what do you think about the 6th problem from the list of 23 problems by David Hilbert, which is about axiomatizing physics? How can it be related to the project?
So basically it's what we're doing, but it's not at all what he envisioned. He envisioned, again, we're going to formalize the one true theory and everything else comes out of that. And we basically say, yeah, you can formalize it, but not like that. So in my mind, we are solving his problem, but not the one that he stated, the conceptual one of axiomatizing physics. Yeah.
The next question is from Xinyue. Usually topology is introduced by abstracting concepts of boundaries and sets on continuous space, like our physical space. What's the connection here with topology introduced from experimental verifiability?
Right, the open sets are the thing that you can experimentally verify. And that basically gives you that notion of neighborhood and closeness. So if you have a point is a possible case. And a neighborhood, an open neighborhood of that point becomes a verifiable statement that is true if that case is true. So a point could be the mass of the electron is 1, an open neighborhood is an open interval between that. That's going to be a verifiable statement. And with this connection, you can re-understand all the notion of limits, convergence, continuous transformations, in terms of experimental verifiability, because now you know how to translate. So it would take time now to do it, but you can absolutely do it. And you would have an introduction to topology that it's grounded in physics.
Next question is from Daryl. Do you see a possible scenario where the foundation axioms are too restrictive? If yes, how do we tackle this problem down the line?
Say it again?
Do you see a possible scenario where the foundation axioms, so our axioms,
our axiom,
I believe our axioms is the intent, are too restrictive? If yes, how do we tackle this problem down the line?
So if it's too restrictive, it means we watch the axioms. But it's going to be true, like this is where having to write the justification actually helps you see whether the axiom is too restrictive or not. Because when you write the justification, you realize, oh, I have to justify this. Where do I get it from? And that's when you realize that the thing that you're requiring is not always going to be there. And if you think that it's always going to be there, and in 50 years somebody realizes, oh, that's not true, then what happens is that you're going to change the axioms to a definition and have the more general axiom. But you are going to be able to, since you have the justification, you're going to be able to make that evaluation a lot more I can say top of the mind, like you actually know what you're doing. While right now you just put a mathematical axiom, you have no idea what is implying, so you can't even know whether it's too restrictive or not. And by the way, it happened to me while I was justifying axioms. I realized that they were too restrictive and that I couldn't justify those. So.
Okay, the last question is from Robbie. In quantum mechanics, we do not measure eigenstates of the position operator, delta Dirac, because we cannot be infinitely precise. Wouldn't it be more appropriate to have a position operator whose spectra is physical states that can be prepared in experiment? And then there's some discussion afterwards about whether we can measure any eigenvalue with infinite precision, but then it's noted that we can measure number of particles, so discrete quantity, and that the number operator is also defined on the whole Hilbert space.
Right. So again, this connects to the Borel sets and so on. Like if you think classically, all your statements are these Borel sets, and then you can check whether something is in the Borel set or not, right? And the point, you can think it as this interval that becomes a closed interval that becomes infinitely small and then becomes and picks a point. The same thing happens in mathematics with the Hilbert space. So what you can do is that you can think of, instead of just a position operator, you can think of all those operator that gives you 1 on a Borel interval and 0 outside of the Borel interval, right? And that would basically mean the particle was within this range or was outside of the range. If you do things mathematically correctly, right, to get your probability distribution, that's what you already do. So, you know, people in quantum logic are going to talk about these projections, and then you have a whole lattice of projection operator. You assign the probability to all these things, and then you get the probability measure, right? And so it's not, it's already done. Let's just put it like that.
That is all the questions in the Q&A. It is 11:27 Michigan time. So you might, I don't know if you want to take a minute
Yes.
between the sessions.
I'll fill in my bottle of water.
Yep.